Hello everyone, welcome to this lecture. So, we will now start discussing about efficient protocols for perfectly secure Byzantine agreement. So, recall that till now we have seen the EIG protocol for perfectly secure Byzantine agreement. That protocol was designed with the condition n greater than 3t, and it was inefficient in the sense that it requires exponential amount of computation and communication. Okay. So, now we will focus on designing protocols, perfectly secure Byzantine agreement and broadcast protocols, where the parties need to perform only polynomial amount of computation and communication. So, we will first see a very simple protocol. This protocol is designed with the condition n greater than 4t. That means, while the EIG protocol can tolerate up to t corruptions where t is less than n over 3, the protocol that we are going to discuss today can tolerate only up to n over 4 number of corruptions. That means, the corruption capacity, the capacity to tolerate the number of faults for the protocol that we are going to discuss today is less compared to the EIG protocol. Okay. But in return, we get efficiency, namely the protocol does not require the parties to perform exponential amount of computation or communication. Okay. And this protocol is based on a very nice paradigm called as the phase king paradigm. In the subsequent lectures, we will see that we can actually improve this protocol further, in the sense that we can design, we can change the protocol and we can tolerate up to t less than n over 3 corruptions. That we will see in some subsequent lectures. So, eventually we will see a phase version of the phase king protocol, phase king based protocol, which can tolerate up to n over 3 corruptions. Okay. So, this protocol consists of t plus 1 phases, okay, and each phase consists of 2 rounds. Okay. And there will be a designated king party for each phase, which will be publicly known. So, for simplicity we can imagine that in phase 1 party P1 will be the king, in phase 2 party P2 will be the king, and in general in phase I party Pi will be the king. Okay. But of course, the parties can follow any other assignment of the kings to the respective parties. The only thing is that we have to ensure that in each phase a designated party, a fixed party is assigned as the king, and the kings are never repeated, in the sense that each phase will have a unique king assigned to it, and the parties will be aware of the fact which party has been assigned as the designated king for which phase. So, the general idea behind the protocol is the following. In each phase k, the parties first try to find out whether all the parties have the same bit or not. Okay. So, for that they will exchange messages with each other, and there are two possibilities, yes and no. If it turns out that in some phase k all the honest parties have the same bit, then we need to ensure in the protocol that the parties stick to that bit, that common bit, in all the subsequent phases, namely phase number k plus 1, k plus 2, k plus 3, all the way up to t plus 1, because what I am saying is with respect to any phase k, where k belongs to 1 to t plus 1. Say for instance, if in the second phase it is identified that all the honest parties have the same bit, then somehow in the protocol we need to ensure that from third phase onwards all the honest parties stick to that bit, that common bit, irrespective of what exactly is the status of the king, whether the king is honest, whether the king is corrupt, what kind of messages king is communicating and so on. So, that is the first property which we will ensure in the protocol. How? That will be clear from the protocol steps. Whereas, in phase K, if it turns out, if the parties somehow identify that all the honest parties do not have the same bit, then they take the help of the king party, so that if the king is honest, then at the end of phase K all the honest parties have the same bit. Okay. So, you see the role of the king comes into the picture only when during the phase K it turns out that all the honest parties do not have the same bit. If they have the same bit, the help of king will not be considered at all, but if all the honest parties do not have the same bit during the phase K, then the help of king will be sought. Now, it could be possible that king is corrupt. In that case, king might confuse different parties by communicating different messages, different bits. But what will be ensured is that if the designated king for the kth phase is honest, then using the help of the king party, all the honest parties will come to an agreement at the end of phase K. Okay. And if they come to an agreement at the end of phase K, right, then when they go to the next iteration, when they go to the next phase, anyhow the condition 1 will be satisfied, because parties have already reached agreement at the end of phase K. So, they will be remaining in agreement at the end of phase K plus 1, K plus 2 all the way to phase T plus 1 due to this property number 1. Now, for the moment assume that both these properties are achieved somehow in the protocol. Let us see that how do we get the validity and the consistency properties. The validity property is guaranteed if we ensure the first condition in the protocol. This is because if all honest parties start the protocol with same input bit, right, then they will stick to that bit at the end of every phase, because the help of king will not be considered at all because of this first property achieved in the protocol. And at the end of T plus 1th phase, the parties will output that common input. So, that ensures the validity property. The consistency property is guaranteed because of the fact that we are running the protocol for T plus 1 phases, and in each phase a unique party is assigned as the king. So, in the worst case what can happen is that the first T phases might have a corrupt king, right. So, it might be the case that P1 is corrupt, P2 is corrupt, Pi is corrupt and Pt is also corrupt, right. So, it might be possible that during the first T phases king is not helping at all to reach the agreement, but as soon as we reach to the T plus 1th phase, we will have a party which is guaranteed to be honest, and assuming that property 2 is achieved in the protocol, the honest king during the T plus 1th phase will ensure that at the end of the T plus 1th phase all the honest parties have the same output. Of course, it could be possible that the honest king which is guaranteed to exist among the T plus 1 kings appear somewhere earlier. Okay. It might be appearing in say phase number 2, then we will be reaching agreement at the end of phase 2 itself. Of course, we have to run the protocol for all the T plus 1th phase, T plus 1 phases, because the parties will not be knowing the exact identity of the honest king. Remember, no one knows the identity of the bad parties and the good parties. They only know the number of parties which can be corrupt, namely only the parameter t will be publicly known. Okay. So, that is a general idea behind the protocol. Now, let us see how exactly we ensure the property number 1 and property number 2 in the protocol. Okay. So, here is the protocol code. So, for k equal to 1 to t plus 1, every party pi does the following, executes the following steps, and when I say every party pi, that means this sequence of actions has to be performed by every party. Of course, if party pi gets corrupt by the Byzantine adversary, then it may not follow the instructions which I am going to discuss below. But if the party pi is not under the control of the adversary, it will stick to these instructions. So, there will be 2 rounds in each phase. In the first round, parties try to find out whether they have the same bit for this iteration, during this iteration or during this phase. So, you can imagine a phase as an iteration, and in each iteration we have 2 rounds. So, the first round of phase k involves the following communication: every party pi sends its current preference bit, which I denote by pref sub I, to everyone. Now, you might be wondering what is the initial value of pref I when we start this protocol, namely the first phase. To begin with, every party assigns its input for the BA protocol, which is B sub I. So, B sub I is the input of pi for the BA protocol. So, in the first phase, pref sub 1 will be B, in the first phase the value of pref I will be B sub I. But in general, when we go to the kth phase, in each phase the value of the preference bit will be updated based on some decision rules, and whatever is the current preference bit for the ith party, it will send to everyone including itself. That is also important. When I say, whenever in the course, whenever I explain a code and we have a step send something to everyone, until and unless it is explicitly stated, it means that the party is sending this message to itself. Of course, you might be wondering how can a party send something to itself. Well, we can imagine that logically inside it is making a statement, inside it is keeping a track that okay, I would be receiving this value from myself. Okay. So, it sends a preference bit to everyone. Of course, if the ith party is corrupt, it may send different versions of preference I to different parties, right. And at the end of the first round during the phase k, what we do is the following: we assign the majority of the received preference bit by V sub k, and in the superscript we have I, whereas if no majority is there among the received preference bits, then we set this value to null or bot or some garbage value. You can imagine bot is like a default is null value, it represents neither 0 nor 1. Okay. So, what is happening here is that pi will be sending its preference bit to everyone, and in the same round it will be receiving preference bits from other parties, because other parties also will be following this code. So, they will be sending their preference bits to pi, and pi will be having n preference bits at the end of the first round. It will take the majority. If there is any majority, that majority value is assigned to V sub k superscript I, otherwise the value bot is assigned. Now, during the second round of the phase k, only the king party P sub k does the communication. No other party performs any communication. So, during the second round, the party P sub k sends its majority bit, which it has assigned at the end of the previous round, to everyone. Again, if the king is corrupt, it may send different versions of its majority bit to different parties, but if the king is honest, it will stick to this protocol code and it will send an identical copy of its majority bit to everyone. Now, there will be no more communication in this phase, the 2 rounds are over. The parties now have to decide or set the preference bit for the next phase. How do they set the preference bit? Each party PI checks whether the majority bit which it has assigned, right, whether that value has been received n over 2 plus t number of times during the first round of the kth phase, right. So, remember PI has received preference bits from several parties, and based on that it has set the value v sub k superscript I. What this means is that PI checks whether this value v sub k superscript I has been received from n by 2 plus t plus 1 number of parties at least, namely if it is received more than these many copies during the first round. If it has received more than these many copies of its majority bit, then it sets its preference bit to the majority bit. However, it could be possible that even though v sub k I is set as the majority bit, it has not been received more than n by 2 plus t number of times. Okay. It is just a majority value, that is all. That means, it has been received only n over 2 plus 1 number of times, that is all. It is not received n over 2 plus t plus 1 number of times. If that is the case, then what the party PI does is that it sets its preference bit for the next phase to the value, to the majority value which has been received from the king, right. So, remember at the end of the round 2, PI would have also received a communication from the king party P sub k, where the king party would have sent its majority bit to PI. Of course, if PK is corrupt, it can send any garbage value, but if PK is honest, then indeed the value which PI receives during the second round of phase k will be the majority bit of the party P king PK. So, PI will set its preference bit to that particular value if its own majority bit is not received more than n over 2 plus t number of times. And then the parties go to the next iteration. Once the parties execute these steps for t plus 1 phases, at the end of t plus 1 phases, every party outputs whatever preference bit it has, that is the output of the protocol. So, this is the BA protocol. Now, we have to show that this protocol satisfies the liveness, validity and consistency properties provided n is greater than 4t. Okay, so, we will do the analysis. So, one liveness property is trivial to verify, right. So, every party, every honest party will have an output after time 2 times t plus 1 delta. Why? Because there are total 2 times t plus 1 number of rounds in the protocol, communication rounds in the protocol, and assuming that the time delay for each or the time period between time period for each round is delta clock cycles, then after this much time where delta is publicly known, the parties will output some value. That means, it will not happen that the parties keep on executing the protocol forever. So, that ensures the liveness property. Okay. Now, let us prove the validity and the consistency properties. For that, we will prove some helping lemmas. So, the first helping lemma is that if all the honest parties, right, if all honest parties have the same preference bit at the beginning of any phase k, then they retain the same bit as their preference bit even at the end of the phase k, right. That means, if already the parties have reached agreement at the beginning of the phase k in terms of their preference bits. Of course, the parties will not be knowing whether they have already reached agreement or not, because they will not be knowing what is the preference bits of the other parties at the beginning of any phase k. But what we are claiming here is that if at all during the protocol execution at the beginning of some phase k, all the honest parties have the same preference bit say b, where b could be either 0 or 1, then the preference bit which the parties honest parties set at the end of the phase k remains the same, namely b. So, let us prove this property. So, since we are assuming that all honest parties have the same preference bit at the beginning of phase k, that means at the end of first round of phase k, at the end of the first round of phase k, each honest party will receive at least n minus t copies of the value b, because every honest party will say that okay, my preference bit is the value b. So, there will be n minus t copies of the value bit of the value b, which will be received by the party pi, every honest party pi. And since we are assuming that n is greater than 4t, then trivially n minus t is strictly greater than n over t plus 2, right. That means, if we go into the protocol code, then every honest party will set its majority bit v sub k I to the value b, and the value from the king will not be considered at all, because every honest party would have received, every honest party pi would have received more than n by 2 plus t copies of the bit b during the first round of phase k. So, that is why they will stick to the value b while setting the preference bit for the next iteration. Now, this lemma immediately implies the validity property for the VA protocol, implies validity for the BA protocol. This is because if all the honest parties start the protocol with the same input bit, that means at the beginning of the first iteration itself they have the same input bit, and during the first iteration the preference bit of every party is its own input for the BA protocol. That means, what we are getting here is that at the beginning of the first iteration itself, all the honest parties have the same preference bit. So, they will retain that preference bit at the end of the phase 1. That means, when they go to phase number 2, they all have again the same preference bit, they retain that at the end of the phase 2, and like that as and when as they keep on going to the subsequent phases, they are not going to change their preference bit, they will stick to the starting bit with which they all started the protocol, and that will be the overall outcome of the protocol, and that shows the validity property is satisfied. Okay. Now, the second lemma, if the king for the phase k is honest, then the claim is that all honest parties will have the same preference bit at the end of that phase. Whichever phase an honest king is there, at the end of that phase the preference bit of all the honest parties will be the same, irrespective of what messages the corrupt parties communicate during the phase k. So, there are two possible cases here while proving this lemma. Case 1, if each honest party uses the majority bit sent by the king to set its preference bit, right. So, if you see the code, there are two possible ways through which every party sets its preference bit. Either it can execute this step number 1 for setting the preference bit, or it might be setting its preference bit through this step number 2. So, the case number 1 is when all the honest parties follow step number 2 during the protocol execution to set their preference bit. That means, no honest party receives more than n by 2 plus t copies of its own majority bit. If that would have been the case, everyone would set their preference bit to the majority bit sent by the king, and since we are considering an honest king for this phase, it will send an identical value of its own majority bit to everyone. It will not send different versions of its majority bit to different honest parties, and since this value is set to be the preference bit for the next iteration, that means the lemma is true. Okay. The other case could be when some subset of honest parties follow step number 1 to set their preference bit, while another subset of honest parties follow step number 2 to set their preference bit during the phase k. Right. Again, that could be possible depending upon what exactly were the initial inputs of the parties and what messages corrupt parties communicate and so on. Right. It is not necessary that if the king is honest and everyone is actually using this step number 2, executing this step number 2 to update their preference bit. One group of honest parties might follow step number 1, one group of honest parties might follow step number 2, depending upon what exactly their state configuration is. We will show that even in this case, at the end of the phase k, all the honest party will have the same preference bit. Let us see how. So, suppose there is some honest pi which executes step number 2 to update its preference bit. That means, it sets its preference bit to its own majority bit, namely the value v sub k I. Okay. Now, let us see the protocol code and argue that why that honest pi would have sent its preference bit to its own majority bit. It is because it would have received more than n over 2 plus t number of copies of this value v, whatever the majority bit it has set, right. That is why it is setting its preference bit to that value v. Now, among these n over 2 plus t copies of the value v which pi has received, at least n over 2 copies, at least n over 2 plus 1 copies would have come from the honest parties, right. So, pictorially imagine that pi has received the value v from this subset of parties, say A, okay, and the cardinality of this subset of parties A is more than n over 2 plus t. Maximum t parties in this set A could be corrupt, but more than n over 2 plus at least n over 2 plus 1 number of parties in this subset A would have been honest. They would have sent the value v to other honest parties as well, including the king p k, right, during the first round of phase k. During the first round of phase k, when every parties are exchanging their current preference bit, pi would have received more than n over 2 plus t number of copies of v. My claim is that among those n over 2 plus t plus 1 number of copies of v, at least n over 2 plus 1 number of copies of v will go to every other honest party. T corrupt parties in A might send different version of their preference bit to different honest parties, but still at least n over 2 plus t plus 1 number of copies of the value v will go to every other party, including the king p k. Consequently, the king p k would have sent would have set its majority bit to the value v itself, because it has received more than n over 2 copies of the value v at the end of round 2. And what is the value which king propagates during the second round of phase k its own majority value, which is going to be V only. So, it does not matter whether any party uses king's versions of the majority bit or its own version of the majority bit, it is going to be V only, and that ensures that at the end of this phase k everyone will be on the same page in terms of their preference bits. Everyone will set their, every honest party will set their preference bit to the value V. Of course, corrupt parties can set their preference bit to anything, we do not care about them, right, and that ensures the consistency property, because as I said, among those t plus 1 phases there will be at least one phase where the corresponding king will be honest, right. It could be either phase number 1 or phase number 2 or phase number 3 or phase number t plus 1. We do not care in which phase the designated king is honest, but in whichever phase the king is honest, at the end of that phase the agreement will be achieved. Of course, it could be possible that in some previous phase itself where the king was not corrupt, where the king was corrupt, but it behaves honestly. That means, even though it is corrupt by the adversary, it still sticks to the protocol code. Well, in that case the agreement would have been achieved in some earlier phase itself. We do not even have to wait for the phase where the king is guaranteed to be honest. That is also a possibility, and in that case from the previous lemma what we know is that once the agreement is achieved at the end of that particular phase, say k prime, then in all the subsequent phases agreement will be still maintained, right. That is what we have proved in the earlier lemma. So, irrespective of whether the help of the honest king is taken or not to reach agreement or not, agreement will be achieved definitely by the end of t plus 1 phases, that is guaranteed here. Okay. So, now let us try to do the complexity analysis of this protocol. How many communication rounds are involved here? 2t plus 2 rounds, because there are t plus 1 phases and in each phase there are 2 communication rounds. So, total 2t plus 2 rounds are involved, and this is more than EIG protocol. So, recall that in the EIG protocol the number of rounds was only t plus 1, but here we need more number of communication rounds. So, that is one disadvantage of this protocol compared to the EIG protocol, but the good part is that the communication complexity is only O of n cube bits. Okay. Why? Because each phase requires a communication of O of n square bits, because every party needs to send its preference bit to everyone else, and then the king has to send its majority bit to everyone else. So, that requires overall O of n square bits of communication in one phase, and how many phases are there? There are t plus 1 such phases. So, we can always assume that t is big O of n. So, that is why the total communication will be O of n cube bits. So, this is the good part, this is the advantage, this is polynomial compared to the EIG protocol. Right. Whereas, in the EIG protocol the communication was of order n power t plus 1. So, you have the trade off here. If you want to reduce the communication, but you are fine to have more interaction in the protocol, you can go with this protocol. Of course, another disadvantage of this protocol is it requires the condition n greater than 4t. So, again a trivia here, why this protocol works only for n greater than 4t. So, it is a homework for you to go through this protocol and assume that say n is equal to 4t and run the same code. and see what happens. Okay. Run the same code and see whether you have the validity and consistency properties achieved in the modified protocol. You will see that it will not be the case. So, the protocol that I have discussed in today's lecture is taken from this textbook. Thank you.